When starting this project, our group began by researching water filters with the plan to make a cost-efficient water filter that could filter out as much dye from the water as possible. We wanted to optimize the size, materials, and cost when we decided our final material list before putting in our first order. This was because we knew a smaller housing would be better because we only had to filter out a small amount of water. And we wanted this to be more cost-effective because we only had a budget of $300 to do so. So multiple trials would be necessary, and we needed money for room for mistakes. Finally, we knew that because we chose a small housing, we would not be able to use as much material, so it was inevitable that we had to optimize our material.
After doing initial research, our first thoughts were to use sand, activated charcoal, cheesecloth, pebbles, and gravel. A few tests later, we realized that this was not going to work, and we went back to researching. In previous tests, we could see that the cheesecloth and sand were absorbing some of the dye, but we knew that those two materials alone could not absorb enough of the dye, so we continued to research more materials that would improve our initial idea. Finally, we found that activated charcoal was very good at absorbing dye, so for our second test, we used activated charcoal, sand, and cheesecloth. For our second test, we found that the water still was not as clear as we wanted it, so we thought about how to maximize the use of the three materials we had just ordered. After testing the charcoal alone, we found that if we thoroughly rinsed the material, it was much better at absorbing the dye, and the longer the dyed water was exposed to the charcoal, the better job the charcoal did at pulling out the dye in the water. So, we resolved to using multiple layers of sand, charcoal, and cheesecloth in the design of our water filter. After testing this design, we found that it worked well, and we thought we were done. Little did we know that we had forgotten to include a stretch element, so we looked through the list and thought about what we could do. After testing the activated charcoal alone, we decided to test if it could filter enough of the dye out of the water so that we could reach activated charcoal is the best for our stretch element. We found that there was little difference when using activated charcoal or both sand and activated charcoal. So, to reach our stretch goal, we decided to stick with one filter material and just use activated charcoal.
Here you can see a diagram and picture of our final water filter. It consists of a housing, end cap, activated charcoal, cheesecloth, and 2 cups. We first drilled a hole into the bottom of the 1-inch end cap so that the filtered water could flow through the pipe, and then screwed it onto the bottom of the 1-inch wide, 6-inch long pipe. Inside the housing are 4 layers of charcoal and cheesecloth, with a piece of cheesecloth inside the very bottom and top of the pipe as well. Initially, we wanted to 3D print a stand, but to be time as well as cost efficient, we used a paper cup instead. We cut a hole out of the bottom about 1 inch wide that fits the end cap and securely holds the housing. This upside-down cup stand is placed on top of another cup that catches all the filtered water. Inside of that cup, there is a line drawn at the 10 milliliter mark to indicate when the collection goal is reached. The total cost of one completed device is $186. This chart shows the exact breakdown of each material's cost, and as you can see, most of our money was spent on the housing and the charcoal, while the end cap, cheesecloth, cups have relatively low costs.
The Arduino code our group wrote collects data from the photosensor, potentiometer, and LED, and displays the photocell value of light intensity on the LCD screen. The Arduino recorded and displayed a light intensity value of 478 for the filtered water from our official test. This value can be used to determine transmittance, absorbance, and concentration with the help of equations and the calibration curve we made. When calculated, the transmittance equals 0.467 and the absorbance equals 0.33. When you compare this absorbance value to the calibration curve, you can determine the concentration of dye in the filtered water to be approximately 0.4 arbitrary units. With the initial dye set as a concentration of 1 arbitrary unit, this means our filter removed 60% of the dye from the water.
Upon arrival to test day, we prepared our apparatus by cleaning our housing and all of our charcoal as to remove any possible soot or dirt that could find its way into the testing water. We had the mass as well as the height of our apparatus measured and began to test. Like we had practiced, we began to slowly pour the water into our housing, allowing a considerable amount of time between each pour in an attempt to give the charcoal as much time as possible to remove the dye before the water exited the housing into our collection cup. Once the 10 milliliters had been collected, we had both our Arduino spectrophotometer and a professional spectrophotometer both give us similar readings that showed us we had removed around 60% of the dye. This had been our most successful trial that we ran, and thankfully it was on test day.